Hello everyone. In this video you are going to see what is DC analysis and how to perform DC analysis for one configuration of differential amplifier. So DC analysis is nothing but to obtain the operating point values for the transistors used. Now here we can see that the Q1 and Q2 are the transistors, and we have to obtain the operating point values, nothing but here the output is taken across the collector. So the operating point is ICQ and VCEQ, nothing but output current and output voltage. So after obtaining the operating point values, here in order to obtain the operating point values, what we have to do is we have to switch off the AC signals. Now in this circuit, the VS1 and VS2 are nothing but the AC signals that we are applied, and VCC and VE are nothing but the DC signal. Okay, in order to obtain the operating point values, we have to make sure that the AC signals are off, nothing but there is no apply of VS1 and VS2 signals. Okay, so here the VS1 and VS2 signals will be 0. After maintaining this condition, we have to obtain the transistor operating point values. After obtaining the transistor operating point values, we have to make sure whether the transistor is operating in active region. Now why we have to consider only the active region? Since we are using an amplifier circuit. Now what the amplifier has to do? It has to strengthen up the weakened signal, or it has to strengthen the weak signal. So this is the purpose of an amplifier. So whenever the transistor is in the transistor operating point is in active region, in that case only whatever the signal that is applied, that is amplified. That's why after obtaining the operating point values, we have to make sure that whether the transistor Q1 and Q2 are in active region or not. If they are in active region, then we have to apply the analog signal to the circuit, in which it will perform correct amplification without loss of signal. Now for this circuit we have to obtain the DC equivalent circuit. After obtaining the DC equivalent circuit, we have to perform a KVL and KCL operations to the circuit in order to find the output current and output voltage. Okay, now how the DC equivalent circuit will be obtained? The DC equivalent circuit can be obtained by reducing or by grounding the AC signals. Okay, this is the DC equivalent circuit that is shown here. If we observe that at this point the circuit is symmetrical. Okay, to this transistor Q1, input resistance is Rs, output resistance is Rc. Similarly for the transistor Q2, the input resistance is Rs and output resistance is Rc. So since the two transistors are matched, so it is enough to find out the quiescent point or operating point for any one of the transistor. Okay, so either for the transistor Q1 you can find, or either for the transistor Q2 you can find. So in order to, since these two are symmetrical, I am considering only the half circuit. Let us say I am considering only the half circuit, that is for the transistor Q1. Okay, now we have to find the collector current for the dual input balanced output differential amplifier. Now consider how the DC equivalent circuit will be for the dual input balanced output differential amplifier. In this, the signals, input AC signals VS1 and VS2 is 0. Now consider only the half circuit. Why? Because these two transistors Q1 and Q2 are matched transistors. So if you perform the DC analysis for the half circuit, it remains same for the another half circuit. Now simply apply KVL at the input of the transistor Q1. So simply apply KVL at the input of the transistor Q1. If you apply the equation, that it is minus VS1 plus IB into RS plus VBE plus 2IE into RE minus VEE is 0. Now from the basic definition of DC analysis, we came to know that the AC signals VS1 and VS2 is 0. Okay, now simply substitute the VS1 value is 0, and from the relation of collector current and base current, we know the relation, that is IC is beta into IB. Since the gain of the transistors are very high, we can write the collector current IC is approximately equal to IE. Now simply substitute this IE in this equation. Then we'll get IE as beta into IB. Now substitute this equation in this equation. So wherever the IE value is there, simply substitute it as beta into IB. Then we'll get the relation like this. Okay. Now common the value IE. So if you common the value of IE from this equation, you will get it as Rs by beta plus 2Re, which is equal to VE minus VBE. Now we can find the value of ICQ as VE difference VBE by Rs by beta plus 2Re. Since we know that the value of beta is very high, 1 by beta value will be very low. So from this we can say that the Rs by beta value is very less compared to 2Re. So in practice or in general, if the Rs value is not mentioned in the circuit, then we can neglect this term and we can obtain the value of output current operating point as VE minus VBE by 2Re. So this condition is valid only in two cases. First case is if there is no source resistance given in the circuit, and the second case is whenever they mention that the beta value is very high, in that case we have to neglect this term Rs by beta. Why? Because since beta is very high, 1 by beta value will be very less, and this value is always less compared to 2Re. So simply we are ignoring this term Rs by beta. So the next we have to find is the output voltage operating point, that is VCEQ. VCEQ. Now let us consider the same half circuit that is considered in finding the current ICEQ. So if you observe from the vector mathematics, we can write this VCEQ as the difference between two node voltages. One is the collector node voltage and second one is the emitter node voltage. So we can write the VCE as VC difference VE. Okay, so now we have to find what is the value of VC and then what is the value of VE, and finally substitute in this equation the individual values to get the final value of VCE. In order to find the value of VC, what we have to do is, first we have to apply the Kirchhoff voltage law at the output side. So if you observe, this is the output voltage. Okay, so one node is VCC and the second one is the voltage drop across the resistor RC, and the third voltage is VC. So if we apply KVL, then we can write the equation as minus VCC plus the voltage drop across the resistor RC, that is ICQ into RC, plus the voltage drop, that is VC. So if you observe the equation, that is minus VCC plus ICQ into RC plus VC is 0. So from this equation we can find the value of VC as VCC difference ICQ into RC. After getting this, simply substitute this in this above equation. So finally we get VCE as VCC difference ICQ RC difference V. Now the next step is how to find the value of emitter node voltage. So this is nothing but VE. Okay, in order to find the VE, simply apply the KVL at the input loop. So if you apply the KVL at the input loop, what is the equation we have to get? So since the input voltage, that is AC signal, is 0, now the current is IB into IB is the current flowing and the voltage drop across the resistor is IB into RS, and this is the cut-in voltage, that is VBE, and here it is the node voltage, that is VE. Okay, now since the transistor gain is very much high, we can ignore the value of IB. So from this equation we can ignore the term IB into RS. So if you ignore IB into RS, we can write the VE as difference of minus VBE. Okay, now we found the value of VE. Simply substitute the value of VE in this above equation. We will get the final expression as VCE is nothing but the operating point. We can write it as VCEQ, which is equal to VCE, which is equal to VCC difference minus ICQRC plus VBE. So this is the final equation, output voltage of operating point for the transistor Q1. Similarly, this analysis is applied for different configurations of op amp. Thank you.